this chalk is like not at all bright, right? At least on the whiteboard. Is it fine? I hope those who were like taking this optimization course, they already have some idea about the optimization, but the remaining ones not. So that is initially that is I thought that is I will cover only that is LMIs. But later I thought that is no, that is if it is only LMI, like for myself as well, when I learned LMI, that is during my coursework at the PhD time, then like I had a lot of confusion. That is all of a sudden why LMI is coming into the picture. That is somewhat that is if I introduce LMI and then if I solve 6 or 7 problems, of course that is you will have ideas about that is how, what is this, like what is a linear matrix inequality technique, why these are useful for control engineers, in for what kind of problems we can apply, then of course for some of the standard control theoretic problems how we can apply the LMI technique for getting a solution. But in what you will have, that is when I learned it also in the same way, but later I had lot of confusions regarding that whenever you learn LMIs or read LMIs from somewhere, immediately along with all these keywords will start appearing. One of the very common is you will find semi-definite programming, SDP, then somewhere convex optimization, somewhere linear programming, LP, quadratic programming, QP. All these are from my experience only. So that's why that is I decided that is when we will learn LMI. Along with that, we must learn a generic overview about the whole thing which is associated with LMIs. Okay, I believe that will also be very useful for all of you. Is that fine? So first of all, you tell me that is here what we are doing, that is optimization, right? Ultimately, this now like at the very beginning, you might have a question, that is what is the relation or what is the connection between an optimization and optimal control, rather robust control. Can anybody tell me that? Here, this is a robust control course, or rather a control course. Why that is we are bringing optimization here? That is the first question.
So while designing the controller, we have to minimize or maximize some cost function.
Very good. Exactly. That is while designing a controller. See, that is again there will come a basic question, that is in our undergraduate we learn PID controller, even lead lag compensator, right? Now, what the hell has happened, that is we have to learn optimization for solving a controller design problem. That is also a basic question, right? We knew how to design a PID controller, Ziegler-Nichols or some other tuning algorithms are there which are standard. Lead lag compensator, that is also there. After that, when we started state feedback design, we learned LQL will come later, Ackermann formula, all these things. But now, what big deal has come up for which we have to learn an optimization technique to solve a controller design problem? Isn't it? That is a very valid question. Yes.
So the answer I was giving.
Uh-huh.
I was giving the answer. I thought you would ask.
Uh-huh. Please tell me.
So sir, that I think in the pole placement and the PID, we just get the controller, but we cannot ensure that that is the best or the optimal controller. We just know where the poles should be, and we just give a pole to make the system stable. But in order to have an advanced controller where we know that that is the optimal pole placement, we need to minimize some cost function to ensure the optimality of the solution. In PID, there is no optimality.
PID can also be designed in an optimal manner, but if we use Ziegler-Nichols or all those kind of tabular things, there we don't have we don't have any objectives such as minimizing or maximizing something. Okay. It is the right point. Can anybody elaborate his point, or Kanika?
Like in optimization, we minimize or maximize the cost function or objective function.
But why it is related to a control problem?
Like in robust control, we design the control that will do their functioning by having some disturbance also. If we give some disturbance to our...
Even in classical control also we have disturbance attenuation problems that you might have studied, but nowhere we solved it as an optimization problem, right?
We need to minimize the error, in that sense.
Some constants are there, like we are try to minimize the whole controller problem with some constants. That's why introducing optimal control. Because as when we are
No,
designing,
this language is not correct. That is, we try to like minimize or maximize the whole control. That is not a correct word. Try to be precise.
Minimize the error.
like as per the request, we have to minimize some. If we are trying to minimize the power or power at a certain time or at some infinite time, that's why trying to impose the like optimization problem.
Okay. Any other ideas?
So
Arun?
in the real life applications, there will be limitations to the input that we can give. So
Like some
incorporate-
constraints.
Yeah, constraints and
Constraints will come later. Like first, what I'm trying to understand from you, that is why should a control problem be formulated as an optimization problem? That is the first question we are trying to figure out. Of course, what you said, that is you were talking about the constraint part. That is when we design a controller, it is not that you can take any values. Mostly that is when we design, most of the cases we think that is the environment is ideal, and then we design a unconstrained, even for the infinite horizon LQR that you have solved. I believe so far you have solved an unconstrained LQR problem. But in practice, this is not at all, it will be an unconstrained LQR. Of course, there will be constraint on the state variables. I mean, how maximum or how much minimum values it can take even, and the same thing would be on the control input. So you have to solve the LQR problem in the presence of those box constraint on the X as well as U, right? So for that we need what? Pontryagin minimum principle or the Hamiltonian approach. It has a algorithm by which we can solve, right? Anyways, like those things are a little bit complicated, it will come later. But first of all, what that is I'm trying to understand, it is why a control problem is required to be formulated as an optimization problem. Why should we do that? Or even if we do that, does it give us any advantage? That is the question. I hope all of you would know that. You have already done that, but I am just like trying to extract it from your mind.
Can you repeat the last part what you were just answering?
That is what Arun said, that is about the constraint. Of course, that is here, the constraints, like when you solve an optimal control problem, if there is no constraint, it is an unconstrained optimal control problem. For example, the LQR, what you solve, that is from the Riccati solution, you write that is U star, optimal U equals to minus R inverse B transpose P into X. That is the result of the unconstrained infinite horizon LQR problem. But if somebody tells you, if somebody needs, that is the the magnitude of the control input would be in between plus minus 5 or plus minus 10, then that is not the solution. Because there, when you solved the LQR, you didn't put any magnitude constraint on the control input, not even on the state. For that is when Sinisar will teach you Pontryagin minimum principle, then you will learn the whole algorithm. Through Hamiltonian approach only we do that. Anyways, I am not going there. What I am asking, that is for any controller design problem, why suddenly we have a requirement of formulating that design problem as an optimization problem? That is my question. Like Sutosham has already answered, but I want a bit more elaboration. What do you mean? Answer is that only. I wanted a further explanation or a bit elaboration. I give you a simple example. You don't have to even go for robust control. In classical control also, I think you might have seen while just learning the error constants. After that, there are some performance indices like IAC, ITAC, IAE. Do you remember? IAC means integral square error minimization. this is nothing but ISA, right? Now you can find the difference between just a PID controller design or a lead lag compensator design, but with some objective function or with a specific objective. Try to understand. That is, every controller will always try to reduce the error, right? But when you formulate that as a specific problem, then your controller would be further efficient. That is the need for an optimization problem, okay? That is, whether you design a PID or a lead lag, it is not that we didn't have any specification or we didn't have any objectives in mind. It is not. When you design a PID controller, what do you generally do? Although we don't go for pole placement, but we impose specifications on the transients, right? Maybe the percentage overshoot has to be less than 10%, settling time less than 4 seconds, peak time maybe less than 2 seconds, and steady state error should be 0. Like all those things, those are called the transient specification. Those things we apply. When we design lead lag compensator, there also we impose frequency domain specifications, like we need 20 dB gain margin, we need maybe 40 degree phase margin and resonant frequency, bandwidth, something like that. So whenever you design a controller without performance specifications, you cannot proceed, because otherwise then how would you design the controller, right? But what I wanted to there only lies my question. That is, when you design controller earlier, you had specifications or objectives in your mind, but never you formulated that controller design problem as an optimization problem. So here we are formulating a controller design problem in an optimization framework. Why it is required, or does it give you any advantage? That was my question. Have you now understood what I really wanted to mean? So whenever you design a controller, that is, especially if it is a tracking controller, always the error, that is ultimately error will reduce to 0, because if you expect a faithful tracking, then at t tends to infinity, the error should also go to 0, right? So that is the property for any tracking controller. But therefore, such, that is, of course, that is one of the objective. But there, that is, we don't impose some other constraints like, okay, it will give you a minimum energy, or it will reach the tracking within some certain finite time period, right? Or there it will be the 2 norm or the L2 norm of the error variable would be minimized. Those kind of extra things we generally don't impose, right? So those are, if you would like to add it, like in the optimal control, you must have heard about the minimum time problem, minimum energy problem, right? Those kind of things. So if you have to do that, then we need to formulate the controller design problem as an optimization problem.
So if we are introducing any other term except the error, then we have to impose the optimization problem.
Even here, like on the error only, like suppose like this is j equals to this one, right? So now that is like, if I write, that is like you design a controller such that this j is minimized.
Then also you have to implement the optimization.
Then like if you say that, that is okay, that is we are going to design the controller so that some objective or cost function is minimized, then it is like the controller design problem we have formulated in an optimization framework. Okay, I am just giving you another example. In case of LQ1, if suppose infinite horizon LQ1, all of you please try to understand, because I know like here we are merging 3 domains. One is optimization, another one is optimal control and ROAS control. So this is like a bit tough, but I'm like trying to explain in a layman's word. Okay, so that's why that is I request all of you to be attentive and ask me questions, because it is quite possible that is you will have a lot of doubt. When we approach the LQR problem, what do you do? That is, you have a LTI plot x dot equals to ax plus bu, y equals to cx, and then the primary, what is the primary condition that needs to be fulfilled? AB must be fully state controllable, right? Then, like, what is the problem statement for LQR? Design an input such that this particular j function would be minimized, right? Subjected to the constraint x dot equals to ax plus bu. So design an optimal control function u star such that this j is minimized subjected to x dot equals to ax plus bu if it is unconstrained. If it is constant, then you have to put some boundary or some magnitude constraint on x as well as u. Like, for example, if you have u scalar, then you can write that is u will be always within u max to u min, specifically if the u is a scalar. But if u is a vector, then you have to write in terms of the 2 norm, exactly. Same thing for the x.
But in optimal control, we only did the boundary condition for the states, not for the input.
Like, so far, that is, you haven't yet started the optimal control with minimum energy or input constraints. Probably that is, Finisher has shown you state constraint,
Yeah.
but input constraint he hasn't yet taken. So input constraint is also about to come. Okay. So if there is no input constraint or not even state constraint, it is completely an unconstrained LQR problem. Okay. But if those constraints are there, then definitely it is a constant optimal control problem or constant LQR problem. What is the difference? If it is unconstant, then initially that is your u belong to Rm. Then unconstrained optimal control problem means you can take any value within the whole Rm, right? And the moment you keep on increasing or you keep on imposing the constraints, then that feasible set of u will start shrinking, right? That is the difference between will start reducing or shrinking. Suppose that is for a 3-dimension case, this room is the whole boundary for you, unconstrained. Now you are imposing some constraint because of which maybe you will find only half of the room is the feasible space. That is the effect of constant optimal control. That means gradually the feasible set of u will keep on reducing. Okay.
Just like optimization, when we are dealing with the constraint sets and then physical point in physical direction, just like that.
The what should I say? That is the not perimeter, the radius of the ball. If you think in terms of a ball, then the radius of the ball will decrease. That's what I said. Suppose if it is unconstrained, then the whole Rm, that you can lie anywhere in the whole Rm, in terms of values. But if it is constant, definitely it cannot lie anywhere in the Rm. It must have some constant in terms of values. Okay. For single dimension case, maybe it is here you have to say, for example, for the inverted pendulum problem, then of course there it has a motor, it has some physical a limit. So how much force the motor can exert, that of course there will be a limit. Maybe that is in between, that is minus 5 Newton to plus 5 Newton. That is called a constraint. It is not that for getting a smooth or a brilliant stability performance, if it is required a 100 Newton force, that will also be exerted. It is absurd for a practical system. That is the meaning of a constraint. Okay. And also that is the difference between a constant optimal control problem and an unconstant optimal control problem. Similarly, constant optimization, unconstant optimization. So once again, that is if I come back to LQR problem, then what do you say? Or what is the LQR problem statement? Design an optimal control u star of t such that this j function x transpose qx u transpose ru is minimized, subjected to now the list of constant. First of all, the system constant x dot equals to x plus bu. You can ask that is, sir, why the system constant is required? Otherwise, there will be no connection between this x or u, isn't it? If I don't write that it is subjected to this linear differential equation or linear non-homogeneous differential equation constant x dot equals to x plus bu, then what would happen? That is, there will be no relation between this x and u. So the result that it will give you, that will be absurd. Because ultimately, when this x and u, they are related by a dynamic system, it is not that you can take any value and x can take any value. So that's why this constant, that is the net constant, the system constant, it is required. Okay. After that, if there are some state constant, like some magnitude constant on the state, and then some magnitude constant on the input. So first of all, constant on x and then on u. Okay. So in that way, this is the list of constants. Okay. So have you understood? Now similarly here also, that is, you always have the error signal E of t. Now if anybody say that is, I would like to minimize the L2 norm of the error signal, then it is a L2 norm optimization problem or L2 norm minimization problem. In that way, that is, if you see Navrat Gopal's or any other like undergraduate book, you will find there are 4 types of optimization problems defined on the error signal only, probably IAC and then ITAE, IAE, one more. I'm not exactly remembering them. This kind of one is the integral square error, another one is the integral absolute square error. Similar 4 kind of things are there. So that is the first point for all control students to understand the relation between optimization and control. Without that, we never faced any particular situation through which we can understand that is okay, our controller design problem can be framed in an optimization problem. Okay, because any kind, that's what here I wrote, any optimization problem has the following structure, that is, you minimize or maximize a cost function, which is also called an objective function, subjected to a list of constraints, right? So when you design a PID or defect compensator, we had the objectives or specifications in mind, but did you ever solve an optimization problem to design your controller? It is not that. Everywhere you remember, we had a thumb rule. That is, like, if it is a PID control, and especially for second order systems, what do you generally do? That is for when you have the characteristic equation a square plus 2 theta omega n s plus omega n square equals to 0. From that is, you can easily find out the zeta and omega n. Then percentage over should you had a formula e to the power minus pi zeta root over 1 minus zeta square. For settling time also you have a formula 4 by zeta omega and something like that. We always, we solve a few algebraic equations to find out the controller parameters, right? Even in the lead lag compensator also, like there, that is like when you have, how did you solve a lead lag compensator problem? Depending upon the GM and the PM, first we try to find the frequency, omega r, that is where you have the maximum PM or maybe maximum GM. From that we try to find out that is what would be the locations of the if it is S plus Z by S plus P, where will be the compensator pole and 0. In that way we first go for the one round of design and then we check the Bode plot of the loop transfer function again. If it is not satisfied, we simply repeat this cycle in that way, right? But nowhere we formulated the controller design problem as an optimization problem. Firstly, that is, if you don't remember the IAC or the other thing, then for the first time you learned formulating a control problem as an optimization problem is in the LQ world, isn't it? But IAC was already there, but it was not that important for us, especially in the undergraduate level. That's why we generally skip those parts. But it is there, you can check. That is, we generally call the integral square error minimization problem. Okay, IAC means integral square error. We design here, actually the controller design purpose is that design the U so that this is minimized. Okay, if you can do that, then you will find that is the controller, it is satisfying one particular objective, not only the tracking. Tracking will of course be there, but how you are playing with the error signal, that is related to how much control effort you are putting. Because always, you see, in practice, if you think about why we are going for error minimization, because if error is minimized, So it will save your time, like the reaching time or the settling time, and also you will find that it will have some impact upon the control energy that you are spending, right? So that's why it is required. Now, after coming into optimal control, you must have heard about the minimum time control, minimum energy control, minimum fuel problem, those kind of things, right? All of them are different type of optimal control problem, but as in general, we call them as different type of optimization problem, or rather, we are using optimization techniques for solving optimal control problems. Okay, is the thing clear? Now let's come back here. Up to this much, do you have any doubt?
Sir, while finding out the correct using PID,
Huh.
so when we use the formulas for omega and zeta and all those, so but in that case also we are solving a least square, or we are solving a differential equation and
No.
then finding out.
Because that is completely based on those empirical formulas for second order. That is also the reason, that is why we try to tune PID for third order or for higher order systems, we face challenge. Because these formulas and this formula like percentage overshoot, settling time, peak time, all of them, they are for up to second order, only for second order systems only. When it is a third order, we don't have closed form solutions. So then either you have to go by the dominant pole approach, or you have to use the root locus approach for finding the pole locations or the gains. So there, that is, we don't generally formulate any optimization problem. But here also, that is, I must mention, you should not think that is the PID design cannot be done in an optimal manner. It can also be done. Like there are algorithms, right? Robust PID design or optimal PID design. What does that mean? That is, you have to design the KP, KI, KD so that it satisfies some extra performance, which is not generally expected if you simply follow the Ziegler-Nichols. That is the difference. Now, in state feedback also, when we just go for the Ackermann, what is the Ackermann? Although that is a very handy method, but and also like easy to implement and easy to understand. But what is the limitation? You have to provide the closed loop pole locations, right? Now immediately the question will come, how would you select the closed loop pole locations? Now you have to find the zone, right? And for the zone also, if it is a second order system, depending upon that zeta and omega n, you can find the region. But suppose it is a 10th order system, how would you choose at least 5 pair of complex conjugate poles? So that's why we often go for LQR. But in LQR also, there we have the difficulty for choosing the weightage matrices Q and R, right? Although that is for any type of Q and R, it will give you some optimal performance because subjected to a particular Q and R, this J is minimized. That's what the LQR guarantees. But now how good performance you can achieve in the, how good means in the sense of, that is like always there would be a trade-off between the transient performance and the amount of control effort that you are spending. That every optimization problem, that is, this optimality means there would be a trade-off between, that is, how much like better performance you can expect, and then how much would be the cost. In the LQR also, that is, if you wish the like brilliant smooth trajectory, that for which you will find the control effort will be huge. That may not be possible for all practical systems because always there will be physical limitations on the actuators. So you have to go for a trade-off. Trade-off means now if you have to reduce the if you have to reduce the control effort, then what will happen? The transient performance on the transient which you are expecting, there you have to sacrifice or compromise a little bit. That is a trade-off. So that is the reason why for the tuning LQR, like Q and R, generally we keep R equals to 1 or an identity matrix and we play with this Q because like tuning R and Q together, that is really a trouble, right? And then here you might have seen the Q, if you increase the weight, then what does it mean? That is, it is like the making the dynamic response better. That is, you will find the damping would be more and also the speed would be quite good. But at the same time, that is, if you increase your Q, keeping R equals to 1, you will find that is the U value also is increasing. So that's why that is that if you expect there's a better transient performance, and if you go for like better, at the same time you will find the input cost. Here the cost means that is how much input energy you are spending in terms of magnitude. That will definitely increase. So the optimality means the trade-off you have to decide, that we cannot mentally decide. That's why we solve an optimization problem, so that mathematically that point is decided where you have certain degree of performance. At the same time, the input will also be within a bound. That is the meaning of an optimal control problem, okay? And we solve it through an optimization. Okay, that is the basics. Now that is coming back to the general optimization, because here the LMIs means that is mostly we have to understand the meaning of convex optimization, and a particular type of convex optimization is the SDP, which is called semi-definite programming. Okay, those things we have to understand. First, that is today I am not going to explain each one of them. First I am going to give you an overview, then I will first give you two specific examples of LMI so that your interest develops. Okay? After that you yourself will find the interest to dig up more about all the topics. Okay? Now, that is, can anybody tell me that is, now this is the general structure of convex optimization, right? Now here we have a cost function and then constraints. So depending upon whether your cost function is linear or non-linear, and then whether your constraints are linear, non-linear, we have different type of optimization problems, like, right? Then in a nutshell or in a very easy way, can anybody tell me that is what is a linear programming problem, LPP? Very easy, just you apply your mind, you can easily find out. Or I have already given you the answer, the hint. Constraints are also linear. That is an LPP problem. Once again, if your objective the cost function is linear, say for example, we minimize C transpose X. That is the general format, right? The X mean X1, X2 up to Xn. That is the decision variable which we'll have to find, and C is given. C is, you can say this is the weight. That is how much, that is the weight. Suppose for 3x3 case, if the C is simply 1, 1, 1, then it is the means the contribution for X1, X2, X3, all of them would be equal. But suppose if I write, that is it is 1, 2 and this is 0.5, then accordingly the optimization problem will be solved. That means relative weightage or relative strength of the different variables. Okay, that is the meaning of this C vector. It is given, but this is the decision variable. That means which is the output we are expecting. That is not known. In the C, it is known, and in the constants, everything would be known. Which is the unknown? Here, this optimization variable, or in terms of LMI, we call LMI variables. Okay, or the most common name is decision variable. This is decision variable, which is the outcome of the optimization problem. Okay, remaining all things unknown. So, if, what did I say? If your cost function is linear and your constants are also linear, then it is an LPP, linear programming problem. Okay? Can anybody give me an example? ছিল ওখানে সব, না সবই তো ওখানে আপনার মানে ঢুকিয়ে দেওয়া হয়, যে তামিরা ম্যাডাম বলেছিলেন যে ওখানে ওই সুইমিংয়ে আমি যেটা ছিল সবই দিয়ে দিয়েছি। হ্যাঁ, সেই জন্যই আপনি দেখছেন যে এমনি লিকুইড আর কিছু নেই। আচ্ছা, হুম হুম, ঠিক আছে ঠিক আছে, আমি ট্রাই করবো। হ্যাঁ, বাবার অবস্থা তো একদমই ভালো নয়, ওই সেই জন্য তো বাবা বহুদিনই আর ব্যাংকে যেতে পারেনি আর কি, এখন তো আপাতত বাড়িতেই আছে। আর যেহেতু আমি কলকাতায় থাকি, হ্যাঁ মানে বাবার যখন অ্যালজাইমার স্টেজ 3, ওই জন্য মানে খুবই সমস্যা হচ্ছে, মানে বাবা নিজে ব্যাংক বা অন্যান্য কিছু মানে নিজে অপারেট করতে পারছে, খুবই প্রবলেম। হ্যাঁ হ্যাঁ হ্যাঁ, গুয়াহাটিতেই গেছে। ঠিক আছে, হ্যাঁ হ্যাঁ অবশ্যই, ঠিক আছে, হ্যাঁ ওকে। Any example?
So generator scheduling problem.
How?
Total output of a generator for 2 generators has to be optimized, and both of these have some constraint. Like a generator 1 should have output between these two values, and 2 should have output between these two values.
Here a simple example is what is said, that is generator paralleling problem. I hope those who are from EE background, all of you that you must have read the generator parallel operation in your machines in third year undergraduate. And what is that problem? Like suppose in whole Guwahati, that is the requirement is 30 or suppose 50 megawatt. Okay, that is the requirement. And now, like during in our this power plant, you have the alternator 5 or 6 alternators. Okay. Now, what happens that is like never they are run. It happens that is all of them would be run on full load, right? Because first of all, that would generate the huge electricity, and economically that is not viable. Generally, what is done? That is, suppose if there are 5 or 6 alternators, the proportion would be decided. That is, maybe one would be operated at 60%, another one would be 70%, maybe another one 55%, depending upon the requirement, also the condition of that machine and some other requirement. Okay, so this kind of scheduling one, that is in short, it is called a generator load scheduling problem. So that is an example of a LP. Okay, in that way you can think about. Now, that is here at this moment what I am doing is I am giving an overview, okay? And then that is what happens if your cost function becomes quadratic. Again, now all of you know that what is the meaning of a quadratic function, x transpose qx, right? So, if it is like in your cost function is quadratic but the constants are all linear, then it is the second category QP. Are you getting? So these two are really easy to understand. That is the LP and QP. But for the other ones, we need something more to understand, like SOCP, the second order cone programming, and then SDP, semi-definite programming. So more or less they are related. For that we need some other things. So that's why I'm not readily going there. Okay. But please be informed, as I wrote here, this is a hierarchy of convex optimization problem. That is, all of them are different classes of convex optimization. Okay. So now the main question is that, what is a convex optimization problem? Can anybody tell me that? So I have 3 questions for you. That is, what is a convex optimization problem? And then that is, how it is related to semi-definite programming, and of course, like what is a convex optimization problem, what is a semi-definite programming problem, how they are related, and why we are learning LMI. These 3 questions, can you answer?
Optimization of the convex function is a convex optimization problem, and convex function means if for some two variable x and y, if f of alpha x plus 1 minus alpha is less than equal to alpha of f of x plus 1 minus alpha into f of y, then in this form we
Mathematically that is correct, but now suppose like if I say that is you said the definition of the convex program, but from that we cannot understand that definition in a easy manner, right? So this is one answer, that is what Aditya gave, that is if somebody asks you that is what is a convex optimization problem, then you, both of your cost and your constraints, they have to be convex. If that is there, we call it as a convex optimization problem. Okay. Now the question is that, like before discussing the context, that is if somebody asks you that is why this domain, convex optimization, is so popular, that is a question, right? That is, you will find that is even our like data science faculty members, our communication faculty members, everybody that is needs convex optimization, everybody needs that. Why that is so much important, or why it has applications in different disciplines?
because it has a global minimums. Only a global minimum, like for all local minimums and global minimums.
That is, if there is if any local minima is identified, that will also be a global minima. That is one of the main advantages of a convex optimization problem. Like last day, that is, I was discussing, I said that is what is the main limitation or disadvantage of the meta-heuristic algorithm. You can get multiple solutions. Mostly they will be suboptimal. There it is really difficult to find a global optima. But if your cost function is convex, that means if you can formulate a problem in a convex optimization framework, then your first advantage will be the solution. If it is a feasible problem, then the solution you will get, then it will be a global solution as well. Secondly, you don't have to take the headache of solving that problem, because if it is a convex problem, it can be formulated using the semi-definite programming, which can be easily solved by SDP. Sorry, by LMIs. That is the relation. I will repeat, don't worry. At this moment, that is, there are, I know, lot of queries are coming up. One by one, they will be clear. When we will start taking up the examples, then it will be clear. Like first of all, that is here, you from this Venn diagram, at least it is understood that SDP is one particular program or one particular case under the convex optimization. Before that, you understood that what is a convex optimization problem. That is, although still we don't know what is a convex function, but if we assume for the time being that is okay, we know what is a convex function, then the class of convex optimization problem means for which both your cost function and the constraints are convex, right? Huh? Keep. Did you? Oh, sorry. So now that is under the convex optimization, there are all these categories like the LP and then QP, SOCP, SDP, and CP. Okay. Now here again, we are specifically focusing on one particular thing, SDP, semi-definite programming. Again, a why question will come. Then sir, why you are like so biased about SDP? Can anybody tell me? So far, what we have understood that SDP is a particular class under the convex optimization problem, and that is actually most famous for many of us from engineering disciplines, even for operational research as well. But why? In my understanding, like the although we still don't know what is a semi-definite programming means all this constraint, like first of all the objective, that is a convex function, okay, and then the constraints, they can be expressed by some symmetric matrix relations in the form of fx greater than equals to 0. That is a SDP, semi-definite. You see, from this only the term semi-definite comes. Now, how it can be expressed? So, this is nothing but this fx is expanded like f0, which is a symmetric matrix n cross n. Okay, symmetric and also positive semi-definite. then f1 into scalar variable x1 plus f2 x2, okay, up to fn xn. Fn xn greater than equals to 0. Here I should write where fi equals to fi transpose greater than equals to 0 for all I 1, sorry, it will start from 0. 0, 1, 2, up to n. Are you getting? So what did I say? Semi-definite programming means for this particular class of optimization, complex optimization problem, the constraints can be expressed in this form, from which actually the term semi-definite comes. And if it is so, it is really easy to solve by the LMI's technique. Immediately the question will come, they said, okay, we can understand that if it is expressed in this fashion, you are saying that it can be solved by using the LMI techniques. Then what? Why should you be like so happy? Any answer? Nitisha? तुम्हें तो पता होना चाहिए.
Because we have tools to solve LMI like CBX and other tools, MATLAB tools are there to get one optimal parameter for that equation, that semi-definite equation. So
That is not, it will be confusing for them. Yes, what she said, that is, do you remember, like few minutes ago I said, that is, if you can formulate a control problem in complex optimization framework, then for solving you don't have to take the headache. Why? Because these LMI techniques for solving a system of LMI, say for example, that is, you have a set of linear algebraic equations. How do you solve it? Gauss-Seidel or Gauss-Jordan, those methods, but hand-driven methods are not very easy. Now, that is, you have the MATLAB and the other things by which you can solve. If the MATLAB wouldn't have been there when it was not there, definitely it was like really time-consuming and tedious for us. If you have 3 or 4 algebraic equations, still we can manage. But if it is 10, 15 or 20 simultaneous equations, then really it's a headache. Right? Unless we have a software. Here also the same thing. Suppose like you have the LMIs, for example, that is the PA plus A transpose P less than 0. For today I will show you, that is, if it is a 2 by 2 or 3 by 3, you can still find. But if it is 10 by 10, then really it will be headache. We cannot do it by hand. But if there are some softwares available and commercially available, then it is not our headache, right? That is what she wanted to mean. That is, for solving the LMIs, there are softwares. Who were there? First of all, MATLAB LMI solver. Then other third-party plugins. What are they? One is CBX, another one is Sedumi. Again, there is eAlmim. Anything else?
Is Cassidy also used for it?
Cassidy,
By Cassidy, we can solve, I think, non-linear optimization problems also, but they are for all linear optimization problems. Here are also Gurobi, Mosaic. Now, generally Gurobi and Mosaic, they are not that popular because they are not free.
Some software Jupyter is also there.
Jupyter Notebook. Jupyter is there, but I don't know that is how much. I heard that is there also, that is some mathematical programs are there, but I don't know how much they can do. But of course, Cassidy is there.
but Jupyter cannot be used in
Separately you have to use,
the
but here.
Python programming is
Yeah,
quite
in
fast.
Python.
Yes, the good point. What I like forgot, all these plugins or all these solvers, they can be, what should I say? That is, they are MATLAB based.
They are add-ons for Jupyter.
That is, if you know MATLAB, you can easily, that is, They put all these directories on the root folder of MATLAB and then you use the solver. For example, I think there's a CVX or Sedumi, the solver is a SDPT3 solver. You use that SDPT3 solver, you can get the solution. Okay. So now that is, everything can you figure out? Once again, that is, can anybody summarize, especially about the relation between convex, SDP, LMI? Can anybody summarize? Sudarshan?
So if we are able to formulate any control problem in this manner, where we can
In a convex optimization framework, then
sir,
and especially if the constraints are in the form of, I mean, convex optimization, and on top of that, if you can formulate it in the SDP fashion, then that is your job is done almost.
So first you have to determine if the problem is
Convex or
convex
not.
or not.
Then we have to think about that
Yes.
whether that convex problem can be mapped to SDP framework.
Then what?
If it can be mapped, then you just like try to find out what will be, how the constraints can be formulated in the LMIs. But if this is in SDP, already that is you mentally know that is somewhat we can, that is like we can convert the constraints into the as a like this. I mean as a sum of inequalities.
So one more question.
Huh.
Is shouldn't be f naught x naught, or we're assuming the x naught is 0.
That is 0. That is here
So
is
it's
an
one,
A.
one.
No, here actually the x is a n cross 1 vector. So that's why here x1, x2 up to xn. This is a constant matrix. It doesn't have any relation. Like these are all called affine framework.
Okay.
Affine framework means that is this one. It can be written like f0 plus sum of fi xi greater than equals to 0. These are called affine constraints. Okay. Why affine constraints? We learned affine function means y equals to mx plus c. That is a affine function. Exactly that is its matrix form. So that's why these kind of inequalities or constraints, they are called affine constraints. This is also a term whenever you will learn SDP or convex optimization, LMIs, always you will come across this term affine constraint. This is the meaning of affine constraint. Now, if for some problems, if f0 equals to a 0 matrix, then it will become perfectly linear because the constant term is absent. Okay, so in general, that's why here I wrote linear oblique affine. Okay, so once it is formulated in SDP framework, you know the constraints can be expressed in the as this kind of semi-definite framework, where which are what should I say, a system of linear matrix inequalities, and then you get one of the solvers, you can solve it. So these are the connection. That is why we are like so much interested in learning SDPs and LMIs. Okay. I hope this will help you even in your optimization. This is the overall the broader overview. अच्छा लगा? या नहीं लगा? You knew. Okay, let us take a break. Take a bomb over the This is linear programming problem, right? So whenever you see these constraints, so here we are dealing with mostly linear or affine constraints, right? Now there are again like two categories. One, it could be equality, then it can be inequality, right? So this mx equals to r, this is a equality, and the other one like ax lesser than equals to b, that's an inequality. Now what does that mean? That is, it is nothing but a set of m or n number of linear algebraic equality or inequality. Like that is here, this one if I write, then what it would be a11x1 plus a12x2 up to a1mxn lesser than equals to b1, and then a21x1 plus a22x2 up to a2nxn lesser than equals to b2. Like that only, right? So this is a compact representation, so everything is in terms of matrix and vector. Okay. Now the point which I was about to tell you, that is, if you classify the overall objective function as linear and non-linear. Now you see, you might have a, like initially I didn't mention while drinking tea, this struck my mind. That is, in the context here you have already got QP, quadratic programming. Now quadratic, whenever you have the power of 2, that also belongs to non-linear, right? So that's why here I wrote that is under non-linear, one's special form is quadratic. But you see, that is also convex. So overall, if somebody asks you, that is, tell me whether convex optimization problems are linear optimization problems or non-linear, you cannot readily say whether it is linear or non-linear. Because within this convex framework, you see linear is there, quadratic is there, and now quadratic is a non-linear. That is one important observation, right? So, among say non-linear optimization problems are genuinely tough to handle, but within which there are a few categories. Say for example, one is the quadratic. That can be framed as a convex optimization problems. So, and then that is because of that it has the solution techniques. So that's why if you have a quadratic programming problem, that is still a convex that can be formulated as a convex optimization problem. That is the reason why it comes under the convex optimization umbrella. Okay, but so that's why the takeaway point is that you should not think that is convex optimization, it can handle all non-linear. Neither it is a linear. Okay, so that is one important observation. And so today we are discussing, you see, that is LP you have already understood, QP you have understood, SDP we are now discussing, right? And then once I give you the LMI examples, it will be further clear. Now SOCP and CP, that also that is we have to learn. That is the next day I will define, okay? Because like all together that is I cannot manage in the same day. So here like ultimately that is what you have understood. That is, one is the cost function. That is, for any optimization problem you have two main things. One is the cost or optimization objective function, and the second one is the constraints. Now first you will have to identify that is which kind of cost function you are dealing with, whether this is linear or non-linear. And then that is, once you are sure about whether this is, if it is linear, then of course it can be formulated as a convex optimization problem. So linear means I am talking about LPP, quadratic means this is QP. If it is LPP, of course this will that is come under the convex optimization umbrella. But if it is non-linear, then you have to think about that is whether it is a QP. If it is QP, then you don't have to take any headache, okay? For the other classes. For the other classes still, there is a subset of the others which can be formulated as SDP. Up to that much is still fine. But if you have a problem which doesn't belong to any of these favorable categories, then actually you have to crack your head. Crack your head means you have to go for the nonlinear optimization approaches, which are mostly iterative techniques, and some other you don't have any specific thing through which you can sail smoothly. Okay, that is the important point. Maybe that is I said very quickly. So once again, that is, for objective function, first you will have to understand whether it is linear or non-linear. If it is linear, okay, already for linear programming there are a lot of methods And if you still wish to solve it as a convex optimization problem, that is also welcome, no problem. Now the problem starts if it is nonlinear. If it is nonlinear, first you try to identify its exact category, whether it is a quadratic optimization problem or not, quadratic in the sense of x transpose q, x of p, x, something like that. So when you write a qp function, then exactly in the same way, that is we write minimize of x transpose qx plus c transpose x, because qp doesn't mean that it will only have the quadratic component, it can have a linear component as well. So this, and then subjected to ax lesser than equals to b and mx equals to r. That is the statement of a qp. Okay, so if it is QP, then also that is you don't have to take any headache. If it belongs to the others category, then you check whether it can be designed in the semi-definite programming, in the SDP framework. Here, of course, you will have a doubt, because so far you have already grown a knowledge. You have already seen that is what is the structure of a LP and QP. But since here at this moment I am saying that suppose if it is not LP, it is not QP, it belongs to the other category, but still there is a favorable or less hazardous problems which can still be formulated in a SDP framework. If I don't give you example, you won't be able to understand that is which category is that. I will give you today only, don't worry. But as of now, what I am trying to say, if that belongs to that particular less hazarded category, which can be translated as a SDP problem, then also it is manageable, because here you can see SDP will again come within the optimization framework. Sorry, it will come within the convex optimization framework, isn't it? And once it comes under the umbrella of convex optimization, you have the LMI's technique. Okay? And one thing, please don't think that only SDPs can be solved by LMIs. All of them can be solved by LMIs. Only thing you have to convert them in a LMI fashion. Linear programming. These are generally these are not LMIs, but linear programming problems can be formulated in LMIs. I will show you. Once again, that is, please don't think only SDPs can be solved by LMI techniques. All of them can be solved by LMIs. Only thing, SDPs directly come up, SDPs directly appear in the semi-definite fashion, in the LMI fashion. Other ones readily they don't appear in the LMI fashion. They have to be translated into the LMIs. Okay? So what have you understood? That if it is an nonlinear optimization problem, then also that is we may not have to take a great headache, provided that is somehow we can formulate it as a convex optimization problem. If either it is a QP or if it is a SDP. Okay. So that is about the overview, and now I'm just going to give you two examples, or rather two problems on the LMI framework. Then it will be clear to you. Okay. So any LMI problem means that is you have to understand that whether, and rather you have to verify whether it can be expressed in this fashion, fx greater than equals to 0, where fx can be decomposed in this fashion. Okay. So first we are going to deal with the Lyapunov inequality, PA plus A transpose P less than 0. So many times I said that it can be solved as an LMI problem, but now we have to think that whether really it is a LMI or not. What did I ask? This PA plus A transpose P less than 0. We can check this is linear because P is unknown and A is known. So in that fashion there is no product of two unknown terms. In that sense it is linear. But can it be really translated into this form? Because only then we can claim that it is a LMI. That is the thing we have to understand. Okay? Let's see that. May I erase the remaining things? Afibi, would you come up? वो तो तुम्हें पता है.
but
You? According to the Lyapunov stability theorem for unforced API systems, A is harmonious or the system is asymptotically stable, or the system is asymptotically stable if and only if there exists a real symmetric positive definite matrix P such that PA plus A transpose P less than 0. Okay. Now I claim it to be an LMI, but we have to verify whether really it's a LMI or not. How can we verify? We have to show that the constraint PA plus A transpose P less than 0, it can be expressed in this fashion. Okay? How can we do that? Let us show it for a 2 by 2 example. Okay? Let P equals to P11, P12. It is asymmetric, so that's why in place of P21 I am writing P12 and this is P22. These are nothing but x1, x2, x3, x4. Okay. Since it is a P matrix, so that's why the variables I am naming with P11, P12 like that. So this is unknown. We have to. These are the variables. Okay. So then variables, suppose x1 that is P11, x2 that is P12 and x3 that is P22. Okay. A, this is known, suppose I am getting A1, 1, 1, 1, 2, 2, 1, 2, 2, okay, that is my A. Now you have to find PA plus A transpose P less than 0. What I want to mean, that is whether it can be expressed if x greater than or lesser than equals to 0 or not. Can we express this one into this fashion? That is my target.
But in STP you wrote f of x greater than equal to 0. So you are just posing up, like just introducing a minus
Both of them are possible, right? It depends upon how you are writing the constraints. It can be positive semi-definite
or negative.
Exactly. For all of you, that is, although I forgot to mention that one, it is not that always it would be the positive semi-definite or positive definite. It can be other way around, negative semi-definite or negative definite. Okay. Now you can ask that is, sir, that is, are they equivalent? You see, if you say a matrix M is positive semi-definite, then minus of M is positive definite, that's why they are equivalent. Whenever you are saying something negative definite, that means the minus of that thing is positive definite or semi-definite, okay? So that's why there is no problem in expressing them. Now, if it is so, that is, can I write? P11, P12, P12, 22. Please check whether I am making any mistake. Please keep on track whether I made any mistake. What I want to write, a matrix into P11 plus a matrix into P22 plus a matrix into P12. Okay? That's what I'm trying to write. Because these are the variables, right? If we wish to express f1 x1 plus f2 x2 plus f3 x3, here that is nothing but one matrix into the first variable P11, which is nothing but x1, plus a matrix into P12, second variable, plus another matrix into P22, lesser than equals to 0. Okay? That is the thing I am looking for.
So first matrix should be free of variables.
No. As I said, that is, you may not always have that constant matrix. Here we don't have constant matrix. When it would have, that is, had it been suppose PA plus A transpose P lesser than equals to minus I. Then, like here, if you had suppose minus alpha I, then the constant matrix would have come. Okay? Let's see what is the first one going to be. Here you have 2A11. 2A11 from this term. That is anywhere then P11. Yes, here you have. So P11. What about this term? What are the P11 terms? This one, A12. Any other P11? No. So this is A12. Similarly here also you should expect one A12. And also at the same time, please keep on checking whether they are symmetric, because as we understood, all those matrices should be symmetric, right? So now this is going to be the first one. So this one you can, okay, totally well definite. 2A11, A12, A120, right? Now that is, if I directly write the other one, it has a similar kind of nature. In the first entry there is no term regarding P22. So, and here we said A22. And filling up the last matrix, okay? Here you will have a perfectly 0. And then what about P22 here? In how many P22 terms? Okay, A21. And there A21, fine? Can you tell me whether you are also getting exactly the same matrices for P11 and P22? And now I am going to fill up the middle one. For that, if it is related to P12, then the first entry is going to be 2A1A. 2A21, isn't it? And then what about this one? 2A12. And what would be the off diagonal?
A22 plus A1.
Huh. A22 plus A11, right? Huh. A22. Isn't it? If I designate this matrix as F1 and this is the variable x1, then the second matrix as F2 and this variable is x2, this matrix as F3 and this variable as x3, then how is it going to be? F1 x1 plus F2 x2 plus F3 x3 lesser than 0, right? Or same thing, that is here we can write I equals to 1, 2, 3 A5 x5 less than 0. That's why it is an LMI problem. Okay. And this one, that is we write that is it is an LMI in P equals to P transpose greater than 0. What is the difference between the representation? Here we are describing it in terms of a whole matrix variable, whereas in there we are describing with respect to individual scalar variables. However, but the same thing. Once again, when you are writing in this way directly LMIs, we call that P is an unknown matrix variable, or this is a LMI variable, but when you translate it into this fashion, then actually we are breaking that in terms of the individual scalar variables. Okay. Now the question is, how do you solve it? That is, if you have suppose MATLAB LMI solver or CDX, how do you solve? There you see, of course this is the LMI constraint, and then that is what you were searching for. Before that I should have told you that is this LMI optimization problem, or rather these SDP problems, they are mostly of two types. One is the only feasibility type problems, and the second one is minimization or maximization problem. Once again, these SDP problems, or the initially I wrote LMI optimization problems. So you should not think always you have to optimize something. One is the feasibility problem, another one is the optimization problem. Say for example this one, here we are just trying to find out a positive definite P matrix which can satisfy this Lyapunov inequality for a given A matrix. So this is called a feasibility problem. Here we don't have anything to optimize. But suppose if some minimization is there, like the LQR problem, that is a minimization problem. You will have to minimize the cost function J. So that is the difference between a feasibility problem and an optimization problem. Okay? Now see, in the same fashion, if somebody asks you, that is this linear algebraic equation Ax equals to B, or even linear algebraic inequality Ax lesser than equals to B, both of them can be written in this fashion. That's why LP can be solved using LMI. Are you now getting? This is an LP problem, right? That can be, you have already seen, if you like break it exactly in the same fashion, here you will be getting a constant term. Okay, so both of them can be solved using LMI. The next question is, now that is one very important and really interesting problem we are going to solve, is state feedback design problem. You know, for K, what are the methods you learned? Of course Ackermann and then LQR. Can we design a K matrix for a linear state feedback problem using LMI? Of course we have to take the help of Lyapunov inequality. You think by the time there is, let me erase the board. I'm using only roughly this much. first of all, you tell me that is this state feedback design problem. What is the problem statement? If somebody asks you to describe that problem in technical terms, how would you explain or how would you express it in mathematical terms?
So find the gain matrix
K, right? Very good. Then such that
A minus BK
is Hurwitz. Very good. Find K. Always you have to write that is it belongs to R n cross n such that A minus BK is Hurwitz. Very good. Now you have to take the help of Lyapunov inequality. For the open loop, we wrote PA plus A transpose P less than 0. In the closed loop fashion, what would be? P into A minus BK plus A minus BK transpose into P less than 0, right?
So, as it is described, Lyapunov is describing the contractility gradient, that's why you are using less than 0 such that it will decay, right?
No, here what we are trying to figure out, that is, or we are trying to find a K matrix such that A minus BK is Hurwitz. That means all the poles should be placed on the open left half. Now, that is, if you say the Lyapunov stability theorem, now if I ask you that if you think that A has been replaced by A minus BK, then in this side what you will write?
Okay, you need to become Hurwitz.
Huh. So this side, now in place of A, if I write A minus BK, in the other side also, A in place of A, if I write A minus BK, then here also in place of A it would be A minus BK. But the relation remains the same. That is, you have to search for a positive definite P matrix such that A minus BK is Hurwitz. Now here we are going to deal with two unknown matrix variables. One is the K, another one is the P. That's why it is a bit difficult, and we have to understand how we can handle this. And at this moment we don't know, that is, whether we can handle it or not, right? Have you understood? That is how I am going to formulate the problem. So then first, like, find a K such that A minus BK is Hurwitz. Then if and only if, that means if this is solvable, in that way we have to write, that means you have to write, there exists P equals to P transpose that a real symmetric positive definite matrix P and K belong to R n cross n such that P in place of A I am writing A minus Are you confident with the second line? If and only if there exists please expand the this. You see, at this moment it is not a linear matrix inequality. It is a non-linear matrix inequality, right? Because you have a product of two unknown matrices. Okay? Please be careful about that. Now you have already understood the difficulty, right? See, these are the two terms. Like these are the two terms where you have a product of two unknown matrices P, B, K. Here, like P is unknown, B is known, K is again unknown. Similarly here, K transpose unknown, P of course unknown, but B transpose known. This is the situation. So that's why you cannot call this as a linear matrix inequality. This is a nonlinear matrix inequality. How to handle it? That is now the question. So the main challenge of converting or formulating a problem in the LMI framework is that quite often you will find that although you are dealing with convex optimization problem, but while you are forming them in the SDP framework, some of the inequalities will be in a nonlinear fashion. Have you understood? That means even if you are dealing with convex optimization problems, while you will try to formulate it in the SDP framework, always never it would be very easy to find all of them in a LMI format. You will find some of the inequalities would be in the nonlinear format, and then you have to figure out that how those nonlinear matrix inequalities can be converted into linear matrix inequalities. Okay, there are 5-6 different techniques or mechanisms by which we can convert the nonlinear matrix inequalities into linear matrix inequalities. One of them we already learned before, the Schur complement lemma. Another one is the substitution technique. Okay, there are some other procedures we will run gradually. Okay, the easiest of them is the substitution approach. Substitution approach means suppose your P is one variable, K is another variable. Together you club it as another variable Q, and then instead of solving for P and K separately, you solve for Q. That is called the substitution approach. Okay, but you see here it is quite difficult for us because here the unknown matrices are not sitting next to each other. In between there is an unknown term. That is the difficulty. Are you getting? That is, substitution technique is that if you have two unknown terms sitting next to each other, you can club them as a new variable and you solve for it. But here the problem is, it is not that P and K, they are sitting next to each other. In between there is a known term. Now, as an alternative, you can say that, sir, can't we club this whole PVK as Q? That could be one possibility, whole PVK as Q. But not only solving the LMIs, later on you have to get back those variables, right? So now, that is, if you solve this one, where the variables would be suppose PA plus Q plus A transpose, PA minus Q plus A transpose P, again this is Q transpose. Suppose that is, yeah, you have solved. Then you got if it is a feasible problem for a particular plant, you will get this P matrix as well as Q matrix. Okay, so suppose P you have already got a positive definite matrix, you are very happy. Okay, then ultimately what we are looking for, K, because K is the state feedback matrix. Then you have to think about and how to retrieve this K from Q, whether that would be possible, right? So let's see, in this case, is it possible to get back the Q? So what we assume that PBK equals to Q. Now P is a symmetric positive definite matrix, so inverse exists, right? So it will give you that is Bk equals to P inverse Q. Up to this much it is all fine. But now from this relation, can you find K? That would be a difficult thing.
K is full rank, then you can use pseudo inverse.
B is full.
No, you have to find K, right? So here B is known.
Then B should be full rank. Then we can use pseudo inverse, B inverse 2 equal to K.
Here still you have in that fashion, but many other cases you will find that here that is B may not have the full column rank. B is generally a tall matrix, right? So you may not have always the it will have the full column rank, and even some other cases you may, like in these kind of situations, ultimately, although we have been able to convert it into an LMI, but still lastly we are not done, because there is an immense problem in retrieving the actual thing for which we are solving. So these two are the main problem, or where you need to apply your brain. So what are the two problems in the LMI domain? One is how to convert the nonlinear matrix inequality in the linear domain, and then how to apply the substitution or other kind of things, so that lastly you can find out you can retrieve the LMI variables. It is not that you have solved but you are not able to retrieve the variables. Here we are looking for k, but if you go by this way, either you won't be able to get back the k, or you won't get a unique solution for k. For non-square matrices, mostly we get non-unique solutions, right? That is again a problem, because when we go for a controller design, you cannot say that is okay, we have multiple solutions for the same thing. These two are the main challenges. So first challenge, how you can formulate a problem is in the SDP framework. Second one, of course, you will be getting some nonlinear matrix inequalities, how to convert them into linear matrix inequalities, and also in a way so that ultimately you can retrieve the variables. Okay? Have you understood? This is really, really important. That is not only to convert into an LMI, also that is you have to retrieve the variables. Okay? After that, what should you do? Now you see, is there any way so that we can somehow get P or K next to each other? Is it possible? The technique that we are going to apply is called congruence transformation. What is that? Suppose M is a symmetric positive definite matrix. It can be negative definite as well. If and only if S transpose MS will also remain the same property for any non-singular S. For any called congruence transformation. Okay, we will learn more about that. As of now, I am just only introducing that one. Why? Because what I am going to do, I am going to pre and post multiply that matrix by P inverse and E transpose. Okay, P inverse in between what you have PA minus PBK plus A transpose P minus K transpose B transpose P and then P inverse transpose. According to congruence transformation, if originally it was negative definite, then after this pre and post multiplication it should also remain negative definite, right? And you know that is P is a symmetric positive definite matrix. So P inverse will also remain symmetric positive definite, and thereby P inverse transpose, that means the meaning of this symbol is that is the transpose of the P inverse, that is same as P inverse, which is positive definite as well. Okay. And now that is, if you simplify, then what would happen? P inverse and P, it will be I. So now you are going to have A into P inverse minus B K P inverse plus P inverse A transpose minus P inverse K transpose B transpose. Let we are denoting P inverse by another symbol Y. Okay, it's just a new symbol, it's a different matrix. So in terms of Y, how does it look like? AY minus BKY plus YA transpose minus Y A transpose B transpose less than 0. Are you fine with this? Everyone? Now what is the advantage?
Now we can write
The
AY equal to-
unknown variables are now sitting next to each other. So what we are going to do, this ky we are going to assume q. Now the LMI variables are y as well as q. No longer it is k and p. Please note. So after this, you please follow the chain how I am writing. Okay. From this line here, I am now writing if and only if there exists a symmetric positive definite matrix y and no k. But what now? The new variable q. What is the dimension of q? Same dimension, m cross n. Because k is m cross n, y is n cross n. So q, of course, it will be same dimension, m cross n, such that ay minus bq plus ya transpose minus q transpose b transpose less than 0. Now we are done. So an LMI in y greater than 0 and q. Now directly, see, this is a linear matrix inequality. You can solve it for, now this is still a feasibility problem. There is nothing to maximize or minimize. So you take MATLAB LMI solver or CBX to solve this problem. Now for a particular system, if it is feasible, of course you would be getting the solution y and q. Now ultimately what do you need? K. Can you retrieve k safely? So my q is k into y, and here both these solutions we have got y and q. So now what is your k? What is your k? That is q into y inverse.
while P
But now you don't have anything P. Yes, of course, like here it is a Q into P because Y inverse is nothing but P. So, but what I wanted to mean that if you follow this procedure, then you can safely retrieve the K and there is no chance of occurring multiple solutions. But earlier you have, like you see, that is I could have solved the entire thing at one go. But why I brought all these things into the picture, so that you can learn about that what are the difficulties in the LMI framework. Because many ways, that is even if you after you know the techniques, still we find a lot of problems because there are some nitty-gritties in between. Because when you are when you try to solve the complicated kind of problems or for higher order problems, or even there you have multiple performance criteria, then of course like some of the constants will be in the nonlinear format. And then when you try to convert it into the LMIs, you will find there is many such kind of tricky situations will arise. So that's why you will have to be well aware. Even like this is one kind of the easier problem, then there are many other complicated LMI problems. So we will handle like some of them. Like the main goal of this course is to learn the H infinity control framework or H infinity controller design using the LMI approach. There you will learn that is how very big matrices we have to figure out. Okay, at this moment still it is a kind of static optimization because K is just a game. But there in the H infinity controller, what will happen, that is we would be synthesizing a dynamic controller. So that CS would be, it will have the ABCD matrices. Then in such kind of, obviously it will be a big problem. Then how to handle such cases, right? So I believe after solving these 2-3 examples, you have already understood what is the beauty of LMI and then what is the semi-definite programming, right? So next day we will start with the others and we will learn many different type of LMI problems, okay? And it will, as I believe that it will also help you that is in your optimization course, because there you are learning the things with a different flavor, and like you are learning mostly about the algorithms, that is how to solve optimization problems, and here you are learning some other things. So if you can combine, or if you can if you can bridge the gap between these two, then your learning will be complete. Okay. From your side, what you can do, that is we have learned many keywords like this HTTP and then like LMIs, context optimization. You can search, you don't have to read from Voigt's book, that would be difficult for you. You just in your free time, you sit with your laptop on the internet and you search for some preliminary materials and you go through it. From that also you can learn a lot. Okay?